This is Unit 1, Topic 2, Checkpoint Restart Concepts. Hello, and welcome to the BMC Quick Course series. An early attempt at checkpoint restart was the MVS restart. It is somewhat cumbersome to implement and, in reality, is primarily good for recovering from a hardware failure. You can only restart from the last checkpoint, but you can't make any changes, such as recompiling a program, to fix a problem. Additionally, it is not integrated with any of the databases currently in use today. IMS development got it right when they developed the IMS Extended Restart. Since its introduction, IMS Extended Restart has become a de facto standard for checkpoint restart throughout the entire industry. Compared to the MVS restart, it is much easier, at least from a JCL perspective, to implement than the MVS restart and provides the needed flexibility to support application requirements related to restart. Additionally, IMS Extended Restart is fully aware of IMS requirements. During checkpoint processing, parts of the application storage are captured along with sequential file information. Secondly, the restart point is from the beginning of the program. This allows a program to be recompiled in order to fix a logic-related problem. All database management systems have a variation of a commit or checkpoint. DB2 provides a commit while IMS provides several variations: sync, basic checkpoint, and extended checkpoint. Of these, only the IMS extended checkpoint is a restartable entity. The other variations have too narrow of a scope to enable checkpoint restart. We will discuss this point later in this episode. While they are different, each variation has the following in common: harden data by flushing all relevant data buffers to DASD, releasing any held locks, and physically writing a commit point on the log. Because IMS pioneered the concept of checkpoint restart, let's understand how it works in an IMS environment. IMS Extended Restart supports IMS programs running in a batch region, DLI, DBB, or BMP. Later, when DB2 was introduced, IMS Extended Restart was expanded to synchronize IMS checkpoint and DB2 commit processing. This includes programs that are hybrid IMS and DB2 programs, where some of the data access is in DB2 and some of the data access is in IMS. Additionally, pure DB2 programs are supported when they are set up to execute in an IMS environment using the IMS control program DFSRR-C00. DB2 programs using IMS Extended Restart are not allowed to issue DB2 SQL commits. Rather, they must issue IMS checkpoint calls. These IMS calls will drive the necessary DB2 commits. Now, let's look at the various calls that are used for IMS Extended Restart. The XRST call, or restart call, is where it all begins. It must be the first IMS call issued by the application. Many times, this will be the first instruction of the entire program. The XRST call indicates that this program is a checkpoint restartable program. For normal executions, the XRST call will identify the important parts of application storage that will be snapped at each checkpoint. In the event of a restart, the XRST call can programmatically inform the application that is being restarted. The program might need to branch around some logic if it is being restarted. Additionally, the placement of the XRST call dictates when IMS restart processing will actually occur. This includes restoring the tagged application data to the state as of the most recent checkpoint, repositioning IMS databases, and repositioning GSAM sequential files. After the XRST call executes, the program continues with the next sequential instruction. Now, let's look at the checkpoint call. After the XRST call is issued, program execution will continue and the program will begin to do its normal processing. Periodically, the program will reach a point in the logic where it has completed all processing for a single input. This is called the internal unit of work, or UOW, boundary within the program. When a UOW boundary is reached, the program will issue a checkpoint call and will then resume processing by getting the next input record. Often, to reduce overhead, multiple UOWs will be processed before a checkpoint call is issued. The checkpoint will record the state of the batch job step. It is very similar to periodically clicking the Save button as you develop a document. IMS checkpoint processing includes flushing buffers to DASD, releasing held locks, writing the hex 18 record to the IMS log, which contains portions of application storage, writing the hex 41 record to the IMS log to mark that the checkpoint is completed. After an append, IMS will back out any uncommitted work by processing the log in reverse sequence until it encounters the most recent or last hex 41 record on the log. Once the checkpoint call has completed, database position will be lost, so the program must issue necessary database repositioning calls to establish database position. Now, let's look at checkpoint from the perspective of the IMS log records. IMS logs three types of records that are important to checkpoint restart. The hex 50 records, which contain the before and after images of each update. The hex 18 records, which are the records used for the restart. The hex 41 records, which are the records that mark the completion of each checkpoint. Let's take a look at a log coming out of a DLI execution. For BMP, it will be slightly different but similar enough for our purposes. In a DLI execution, the log will be produced by the IEFRDERDD. In this example, the program appended after completing checkpoint 22. The updates happening before checkpoint 22 are considered as completed. However, the updates happening after checkpoint 22 are considered as in-flight updates. IMS will remove these updates by processing the log in reverse sequence from the end of the log. The hex 50 records that contain the before images will be applied in reverse sequence until either a hex 41 record is encountered or the start of the log is encountered. The log dataset is processed by the batch backout utility DFSBBO00 and will be read via the IMS log RDD to do the physical backout. This is done in a standalone step that executes PGM DFSBBO00. During a restart, the same log dataset is added to the application JCL via the IMS log RDD. The IMS restart module will search the log for the hex 18 records corresponding to checkpoint 22. If it fails to find the correct hex 18 record, the restart will append with the user 102 append. Now let's discuss the differences when running in a BMP environment. The record types are the same for the database change and checkpoint records. However, the log records typically exist on the IMS OLDS datasets. When a BMP region appends, in our scenario it would be at checkpoint 22, the backout would happen automatically while the BMP step is in the process of appending. During a restart, typically the hex 18 records exist on the OLDS datasets and will be automatically inputted to a restart. However, if the restart is delayed for some reason and the OLDS datasets have been overwritten by IMS, the sleds containing checkpoint 22, in our example, would be manually inputted to the restart via the IMS log RDD. Programs that access DB2 often run under control of IMS in order to take advantage of IMS extended restart. The program must follow IMS coding conventions for any IMS calls it issues. This includes the XRST and checkpoint calls. They are not allowed to issue a DB2 commit and will be appended by IMS if they attempt to do so. The IMS checkpoint call will initiate the required DB2 commit processing using a two-phase commit protocol to ensure that IMS and DB2 sync point coordination is maintained. It is the application program's responsibility to reposition both the IMS database position as well as that of the DB2 cursors. Let's take a look at how ARC expands on the concept of cross-DBMS synchronization. ARC accomplishes cross-DBMS commit synchronization by employing the concept of ARC checkpoint, or ARCC-HKP. In addition to the IMS DB2 checkpoint synchronization previously mentioned, the scope of the ARC checkpoint is much larger and allows for a much wider degree of synchronization possibilities. When an IMS checkpoint or DB2 commit is encountered, ARC uses that as a trigger to initiate the ARC checkpoint processing. The ARC checkpoint processing would ensure that the QSAM data buffers were flushed to DASD and that all participating DBMSs would issue their own commit. Some of the more common combinations are listed on this slide. This concludes the training for this module. For more information, please visit www.bmc.com. Thank you.